Hi, welcome back to Chapter 1 Measurements. Okay, today what we're going to do is mainly go through Chapter 1 of your O level or N level science, physics, or physics syllabus. Okay, you can pause the video right now to take a look at the objectives of this entire topic. Okay, moving on. Okay, for in sciences, right, especially physics, right, all physical measurement that we take, right, there's definitely a number to it as well as a unit. So like for example, I am 88 kg, 88 kg. There is a numerical value as well as a unit that is involved. Okay, so all physical quantity have a numerical value as well as a unit. Okay, length. Let's say the my height 1.8 1.8 meter. 1.8 is the numerical value. The unit is meter. Okay, there are different kind of quantities that we measure in physics. First of all, length, very standard meter. Do not write cm, do not write millimeter or kilometer, that kind of stuff. Okay. For mass, we measure in kilogram. I understand that for English, right, uh, some people say like, oh, what's my weight? Okay, Mr. Yong, what's your weight? My weight is 88 kg. But in terms of sciences, right, your weight is measured in Newton, your mass is measured in kg. Okay, this is something that you need to know about English and physics. They don't really gel very well. This is one area that is might be a common misconception for you. Weight is in Newton, mass is in kg. Okay, for time we measure in seconds, not minutes, not hours, not days, not years. Okay, we measure in seconds. Why we use minutes, hours, days, or months or weeks, that kind of stuff, right? Those are easier measurement or easy conversion for easy understanding. But in terms of physics, we always use seconds as our main unit. Okay, electric current, we can use the unit ampere uh, by the letter A. Okay, you'll learn this much later in your syllabus. For temperature, we use Kelvin. Okay, I understand that some of you may think that, but we measure body temperature. My body temperature is 36.9 degrees Celsius. Okay, degree Celsius, right, is a conversion of Kelvin. Okay, at 0 Kelvin, all metals do not move or vibrate. Okay, it's like they don't even move at all. Okay, you learn in lower side that for sciences that object vibrate about solid objects vibrate about in their position, but at 0 Kelvin, the objects in solid don't even vibrate. So that's how we know that they don't vibrate at all. Okay, at 0 Kelvin, no vibration. Okay, how we link degree Celsius and Kelvin, right? This is not really needed for you to know as of now, but degree Celsius is equal to Kelvin minus 273. So let's say I have 300 Kelvin. 300 Kelvin means that it is my maths 27 degrees Celsius. Okay, that's just a very simple calculation. Moving on, next page. Okay, now moving on to something called derived quantity. Okay, derived quantity means, right, like they want to know the SI unit of something that is not common. Okay, so like for example, area. Area, you know the formula in primary school that it is length times breadth. So the unit for length is meter, the unit for breadth is meter. Meter times meter gives you meter square. So that's why your derived unit for area is meter square. For volume, length times breadth times height, meter times meter times meter, meter cube. Okay, next up, density. Okay, density is equal to mass over volume. Mass SI unit is kg, volume SI unit is meter cube. So therefore unit is kg per meter cube. Kg divided by meter cube. So that's why density is kg per meter cube. Speed, you have learned the formula before. Speed equal distance over time. Meter over second, meter over second. So that's how your unit works. Okay, up next, we're going to talk about prefixes. Okay, prefixes, there is one very nice number that you need to memorize, 369. Okay, all the numbers down here are generally 369. Okay, milli 3, micro 6, nano 9, kilo 3, mega 6, giga 9. 369, 369. Okay, centi and deci, I'm sorry, I can't help you with any mnemonics so about it. You have to memorize it. Okay, for nano is represented by the small letter n, and it is 10 to the power minus 9. It is the smallest. Okay, micro is your second smallest, represented by the letter mu. Okay, I'm going to teach you today in terms of how to write the letter mu. Is a line that is diagonal and a letter U. Okay, again, line that is diagonal, letter U. Okay, this is your mu. Okay, it is micro, mu represented by symbol U, mu. The standard form is 10 to the power minus 6. Okay, milli, small letter m, 10 to the power minus 3. Centi is letter C, 10 to the power minus 2. Deci, small letter d, 10 to the power minus 1. Okay, kilo is small letter k, 10 to the power 3. It's getting bigger already. Mega, capital letter M. Okay, why I highlighted milli M and mega M is because mega is capital, milli is small letter. Okay, so mega, 10 to the power 6. Giga, capital letter G, and the standard form is 10 to the power 9. Okay, so what do I mean by why do we need prefixes? Okay, you used to measure, like for example, the width of your trace together token. Okay, you use centimeter. Okay, you measure the thickness of your hair, millimeter. You measure your height, meter. Okay, you measure the distance from our school to Jurong West, kilometer. Okay, so prefixes actually do help to reduce the number of zeros involved. Okay, nano is the smallest, giga is the biggest. So you need to remember 369, 369, centi, deci, memorized by heart. Okay. The distance from the Earth to the Sun is 1.5 times 10 to the power 11. You see the 10 to the power 11 down here, right? The nearest one is that we know of, right? There are prefixes, right? Is giga. Giga is 10 to the power 9. So we can use giga for the distance from the Earth to the Sun. The radius of Earth, 10 to the power 6. Oh, just nice. We can use mega. Length of football field, 10 to the power of 2. 2 is very close to 10 to the power of 3. So therefore we use kilo. The length of a bee, 10 to the power minus 3. We can use milli. The strand of a hair, 10 to the power minus 4. We can use milli or even micro. Okay, hydrogen atom, 10 to the power minus 10. The nearest number is minus 9. We can use nano. Diameter of proton, 10 to the power minus 11. We can also use nano. Okay. There are 4 types of instruments that we use to measure the length of an object. Okay, for example, when you do your PE that time, you take your height and weight. The teacher will usually paste a 2-meter long measuring tape on the wall. Then after that, they can measure your height. Okay, so for measuring tape, right, we generally use it for objects that are larger than 1 meter. Okay, the accuracy of it is about 0.1 cm. Okay, a meter rule, we usually measure things that are less than 1 meter. So therefore, like objects, like for example, the height of your table and such, we use a meter rule. And the precision and accuracy of it is, the accuracy of it is 0.1 cm also. Okay, vernier caliper is something that we use to measure smaller objects, like for example, the width of my hand. So for this, right, why we want to use a vernier caliper as compared to a meter ruler, right, is because it is more precise. It can measure up to 0.01 as compared to just 0.1. I can be more accurate, can be more 准. So that's why I use a vernier caliper. And the range of a vernier caliper is usually from 0 cm to 15 cm. Okay. The most precise object that you have in your physics lab, right, is your micrometer screw gauge. The reason why is because it can measure up to 0.001. It's the most precise. Comparing that of vernier caliper, just 1 0, down here there is 2 zeros. It can be more precise for a micrometer screw gauge. So that's why sometimes I rather use a micrometer screw gauge to measure small objects. Okay. How do we know when to use different instruments, right? It's mainly based on these principles here. Okay. Anything less than 3 cm, micrometer screw gauge. Thickness of coin, I use a micrometer screw gauge. Like for example, maybe the width of my watch is more than 3 cm, but it's less than 15 cm, so therefore I use a vernier caliper. If for example I want to measure the height of a chair, I'm not talking about those high chair, your normal school chair that you're sitting in school, it's less than 1 meter, but the thing is I cannot use a vernier caliper or micrometer screw gauge to measure it because it's too small. So therefore I use a meter rule. Then on to objects like, for example, let's say the length of a classroom. I can't measure using a micrometer screw gauge, impossible. I can't measure using a vernier caliper. The meter rule also not enough. So that's why I use a measuring tape for measuring of classroom. So it really depends on these 4 highlighted points on to know when to use different objects. Okay, different instruments, my bad. Okay. For vernier caliper, there are 2 things that you need to know. First of all, what is your main scale, and number 2, which one is your minor scale. Your main scale is the one whereby the number gaps are very big. So you see this number 2 and number 3, they are very far apart, the scales are all very wide apart. This is your main scale. Your minor scale is one whereby the gaps are smaller. 0 is here, 5 is here, 10 is here, so that's why they are called your minor scale. So how do we read the main scale reading? Let's zoom in here. Number down here is 2. Okay, I know that this is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, 3. Okay, I realize that my red color line, the number 0 of my minor scale, is down here. Okay, I take reference to the number that is on the left of the red line. So this down here is 2.4. So 2.4 is my main scale reading. My minor scale reading is the one whereby my number is aligned, which is right down, which is right down here. This is the number 8. So all I do, I know is that this number 8, I just attach it behind the number 4. So it's 2.48. That is my reading. So therefore, just need to remember reading is major plus minor. 2.4 plus 0. Let me change it in. Okay, which is equal to 2.4 plus 0.08. So therefore, it gives me 2.48 cm. In terms of zero error, you need to make sure, right, that every time you take your reading for your vernier caliper or micrometer screw gauge, you need to make sure that there is no zero error. What do I mean by no zero error? That means my main scale reading and my vernier scale and my minor scale reading, they are exactly one straight line. The 0 of the main scale and the 0 of the minor scale, they are one straight line. Because they are one straight line, there is no zero error. And then whatever reading you're going to take after that, right, is confirmed correct already. You don't need to do any mathematical manipulation to it. Okay. What does it mean by positive zero error? So let me erase all this first. Okay. You realize that the main scale reading, this 0 is down here. The minor scale reading, the 0 is down here. The blue color line is to the right. Okay, it is on the right hand side of the main scale reading. So therefore, this means, right, that there is a positive zero error. Okay, positive zero error. And then now next, we need to find the line that is aligned. We realize that the number line that is aligned is this one down here. Okay, this is 1, this is 2, this is 3, this is 4. Okay, the number that is aligned is number 2. So therefore, like I say again, how to read the main scale reading? I'm going to take this blue line, I draw it up a bit more. Okay, this is 0, this is 0 0.1, this is 0 0.2. Okay, blue color line, go up, find the number on the left, that is 0 0.0. Okay, after that I find my minor scale reading, which is down here. This number corresponds to 2. So therefore, your positive zero error is plus 0.02 cm. Okay, that's it. Okay, this is for your positive zero error. For negative zero error, this is something that a bit more unique. Okay, let me erase again. Okay, for your negative zero error, you realize that your main scale reading, the zero is here. Your minor scale reading, the zero is on the left hand side. Okay, remember I said positive zero error, the minor scale reading 0 is on the right of the main scale reading. This one down here, the minor scale 0 is on the left of the main scale. So therefore now this is a negative 0 error. Okay, negative 0.0 something. Okay, next thing, you need to find the number that is matching. You realize is this one down here. So let's write down all the rest of the number. This is 6, 7, 8, 9. Okay, for negative zero error, this is something very, very, very unique. You need to count backwards from number 10. Okay, 1, 2. This is 0.02. So therefore, your zero error in this case is a negative zero error, negative 0.02, because you need to count backwards. Okay, that's it. Count backwards for negative zero error. Okay, the formula for how we use to find the actual reading of a vernier caliper is actual is equal to reading of the final measurement minus the zero error. So let's say for example I have a reading of 3.69 and I have a zero error of positive 0.46. 3.69 is my reading, 0.46 is my zero error. Actual is equal to 3.69 minus 0.46, gives me 3.23. Whereas on the other hand, if I have a negative zero error, my reading 3.69 down here minus negative, which will give you a plus 0.46, it gives you 4.15. Okay, negative zero error causes your actual reading to be larger. For no zero error, 0.00, nothing happened. Okay, your actual is equal to your reading, full stop. Okay, so right, make sure that you memorize this formula down here, because this will help you a lot. Okay, the previous part we mainly talked about how a vernier caliper works. So now for this part down here, right, we're going to be talking about how a micrometer screw gauge works. Okay, so like I said previously in the vernier caliper portion, that we need to memorize this generic formula, which is actual equal to reading minus zero error. Okay, for the usage of the micrometer screw gauge and the vernier caliper, right, it's actually very similar. You need to know, first of all, you need to have the main scale. The second step is the minor scale. Okay, you can't go wrong if you just keep memorizing main scale, minor scale. Okay, the main scale is the thing that you are not turning. Okay, the one that is not being turned, this one never turn. Okay, the minor scale is the one that you are turning. Okay, so your main scale reading, how you read it is, you realize that this is 0. Sorry, I should change color. This is 0 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. Okay, you record the last number that you see. Okay, this is 4.5 mm. Okay, 4.5 mm. Next thing, you turn on to the minor scale, which means we are looking at this part. Okay, we're going to look here, the line that coincides with this is 10, 11, 12, 13, 14, 15. Okay, the number that is aligned to it is the 12, which is 0.12. So therefore, how we do it is that reading is now equal to the last number that I saw just now, the main scale, it is 4.5 mm. Your minor scale, you plus 0.12. Okay, this will give you 4.62 mm. Oops. Okay, 4.62 mm. Okay, remember main scale plus minor scale. This is your main, this is your minor. Okay, so that's how we get 4.62. Okay, now let's talk about zero error. Okay, I realized that for this one down here, right, the zero is below this line, so therefore this is a positive at zero error. And we realize that the number that is positive zero error, this is 1, this is 2, so therefore the zero error is 0.02. My zero error is positive 0.02. Now to go and find my reading, I go again here, I read my main scale reading first, which is 0, 0.5, 1, 1.5, 2. I know that my main scale reading is, my main is equal to 2.0 mm. Now I need to find my minor. Is the number that is coincide down here. This represents is equal to 0.37, 35, 36, 37, 0.37. So therefore the reading is equal to 2.37 mm. Okay, 2.37 mm. I need you to highlight positive zero error 0.02, reading 2.37. I realized that I need to use this formula again, the one that I've been nagging to you. Actual equal to reading minus zero error. Two 0.37, 0.02. So minus plus 0.02, it gives you 2.35 mm. This is just press your calculator, can't go wrong. Okay, press your calculator at the time. Please remember to include your bracket also if you need help. For zero error, you see again, just now for the positive zero error, the zero is downstairs. Now the zero is upstairs. So therefore now it is a negative zero error already. And you need to count backwards also. So you see, I count 1, 2, 3. Negative 0.03 mm. Count down backwards. If it is negative, always count backwards. Positive, just count as per normal. Okay. Negative must count backwards. Okay. Now to measure the actual reading here, I know that this value is 0, 0.5, 1.0, 1.5, 2.0, 2.5. Okay, main scale, main equal to 2.5 mm. Okay, the line that coincides down here, this is 0.37. So therefore I know that my minor is equal to 0.37 mm. So therefore reading is equal to 2.87 mm. Okay, so like I say again, this is your zero error, this is your reading. Actual equal to reading minus zero error. 2.87 minus negative. Okay, now 2 negative, this one down here, it becomes a plus, so therefore the answer is 2.90 mm. Okay, that's mainly it for the negative zero error for your micrometer screw gauge. Okay, take note that when you use your micrometer screw gauge at time, you cannot over tighten it. You cannot squeeze the thing until keep turning. You cannot. When you hear one click, you must stop it already. Okay, and you also need to make sure that there is no dirt in between the jaws of the micrometer screw gauge, because if there's any dirt, it actually affects the accuracy and precision of it actually affects the accuracy of the object. Okay, just make sure that you don't over tighten it. Once you hear one click, enough already. Okay, I will quickly summarize how a pendulum works. Okay, first of all, I need to introduce the definition of what a period means. It means that the time taken for one complete oscillation. Okay, what do I mean by one complete oscillation? It means if my object is originally at A, you have to go to B, go to C, go to B, go to A. So the whole must complete one whole cycle. Completing one cycle, or one in your proper physics term, is called complete one oscillation. But if you don't understand it, it means one cycle. Okay, so right, it's either A to B to C to B to A, or if I'm going to start at B, I go to C, I go to B, I go to A, I go to B. So this is my second example. If my third example, C, go to B, go to A, go to B, go to C. So that's my third example. These are just generally how a pendulum works. Okay, it's always one complete cycle, must go back to where it originally was. Okay, the main issue with time, right, is actually human reaction time. Okay, human people, we have a lot of error lah. Okay, if I'm going to throw a ball at my grandmother's face, okay, I tell you, she cannot catch a ball because her human reaction time is very weak. But if I'm going to throw a ball at, like, let's say a 15-year-old kid, okay, you all generally can block the ball, that kind of stuff. Okay, the reason why is because, right, your human reaction time is much faster as compared to that of old people. If I'm going to grow old next time, like 80 years old at the time, then all of a sudden I see a durian dropping on my head, I don't think I will have the human reaction time to run away from the durian. I think if I were to be now, I think I can still run now. Okay, it's mainly because of the human reaction time. Old people lag. Okay, so right, for pendulum, right, you just need to remember the cycles which are all stated down here. You need to memorize it. Okay, the things that affects pendulum, right, is if I have a longer string, it will be a longer oscillation. Okay, shorter string, faster oscillation. The mass of the pendulum bob does not affect the period in any way. Okay, so the only thing that affect, right, is length. Nothing else will affect, only length affects. Okay, longer string, slower oscillation, shorter string, faster oscillation. So that's mainly it. Okay, thank you. So if not, give me some time before I upload the next chapter. Thank you.